Welcome back to this third installment of the first lecture one, where we're going to look at E and the natural logarithm. Now, please remember that although we don't do E and natural logs in core mathematics, all of your knowledge of core mathematical logs work will come into the fore here. So make sure that you know your log work from core maths really, really well. We don't need to go into too much detail. E is a constant number. And it is the base of the natural logarithm. So the log of x to the base e, we really just write as the ln of x, and there is no need to write the base, but of course we know that that base is e. And then here, if we just look similar to core mathematics, where we've got the exponential and the log graph both being inverse functions of each other, y equals e to the x, blue graph, it's got that nice exponential curve, y equals the ln of x, the log graph. Inverse functions, remember, the x's become the y's become the x's, domain becomes the range, and vice versa, and both graphs are reflections of each other about the line y equals x, which is quite important. So first graph we're looking at, sketch f of x equals 2 times e to the negative x minus 1. This is quite similar to what we could be asked in core mathematics. We could be asked, for example, draw 2 times 3 to the power of minus x, to the power of minus x minus 1. Think of it like that. So we know that negative 1 is going to be the horizontal asymptote. If I was drawing 2 times 3 to the positive x, so if this horizontal asymptote here is y equals negative 1, I know that my graph would have this kind of general shape, but this negative x tells me that I'm reflecting about the y-axis, so my graph will look something like that. I know that's a really crude drawing, but let's go and have a look. You should be able to unpack what the sketch looks like based on your graph transformations from core mathematics. So we get the general shape. Remember, this negative 1 over here is my horizontal asymptote, y equals negative 1. Very easy to find the y-intercept, make x 0. Anything to the power of 0 is 1, so you've just got 2 minus 1 is then the 1. And then here we've got to go and say, how do I find the x-intercept? Well, there's nothing new here. You make this expression equals to 0. Okay, take the 1 over, divide by the 2, and very quickly we'll be able to take the e over, so it's the ln of a half, and then the x is going to be 0,693, and of course you'd round off to whatever number of decimal places the examiner asks you. But that is an important part of any sketch. Always the x-intercepts, the y-intercepts, any asymptotes, any salient or turning points. Okay, so not too difficult over here. Remember, we actually don't need to show all of this working. We are encouraged to use a calculator as soon as possible. So even from that point, you can go and click the shift solve, and you'll be able to get your x value. Okay, let's go look at this log graph. Now this is an interesting one. So we've got to apply our knowledge of basic transformations as well as the absolute value. Please remember that the standard exponential graph cuts there at 1, and therefore the standard log graph is going to be cutting at 1 on the x-axis as well. So when we go and look here, we should be saying to ourselves, hang on, this is f of x minus 2, which means my graph has now been shifted 2 units to the right. So applying our understanding of transformations from core mathematics then says, instead of the y-axis being this vertical asymptote, it is now shifting 2 units right, which means now x equals 2 is this vertical asymptote, and then we would have drawn this nice log shape, but because of the absolute value, which is going to return a positive, we know that any part that is underneath must then be reflected about the x-axis. And that's a nice application of our knowledge of logs using ln, and then of course playing with absolute values. Just remember, in terms of our definition of the absolute value, the inside is either going to be positive, which would be this branch over here, or that reflect piece underneath also could have been a negative, which is that component over there. Okay, example 3, go and sketch this. Now, I hope you would look at this and say, oh my word, this looks really crazy. I've never seen something like this, especially the transformations at the bottom. Well, then you slow down and you try and take a graph that doesn't look recognizable and rewrite it so that you can apply the transformations. So say to yourself, what are the basic log laws that we've learned? And one of them is to say that this coefficient can become the power. So the very first thing we do is bring that -1 over, and that will invert the whole fraction. Then, of course, if you've got a single denominator, divide each term by that denominator. And now we're starting to look at something a little bit more user-friendly. Then we go and say to ourselves, all right, go through the basics. X-intercept, Y-intercept, any asymptotes. Can we play with domain? Well, yes, we know from our definitions of logs is that this number over here must always be positive. So we say to ourselves, well, the domain, if this must always be positive, 3/2 minus x must be greater than 0, means that x must always be less than 3/2. So when I go to the graph, I definitely can go and draw a vertical line and say the graph is going to be to the left of this 3/2. You might be wondering, how did I get these other two values? Well, not too difficult. To find the y-intercept, I make x equals to 0. And so over here, the ln, okay, the ln of 3/2 is 0,405. And then how did I find this x-intercept here? We just said to ourselves, well, how do I find the x-intercept where y is equal to 0? So let's say, well, then 0 is equal to the ln of 3/2 minus x. Well, then, if you've got this base e, convert this e to the power of 0 is then going to be 1 is equal to 3/2 minus x. Take the x to the left, 3/2 minus 1, which is a half. And it's very easy to then show that the x-intercept is a half, the y-intercept 0,405. You know that you're working to the left of this vertical line, x equals 3/2, and then we can go and draw the sketch. Just another little thing, I don't always like to promote this in class, but when all else fails, generate a couple of points on your calculator using table mode, and that will also help you to visualize what the graph is looking like. Now let's play around with our knowledge of inverses. So we start off, if we asked to find an inverse, step 1, swap the x's and y's. Step 2, make y the subject of the formula. And here we're going to use our knowledge of ln and e. So over here, step 1, swap the x's and y's. Instead of y equals, I've got x is equal to. Then I'm going to bring the 1 over and divide by 2. So I'm now rewriting as e to the negative x. E to the negative y. To get this y on its own, I must take this e over to make it the base, which means it becomes the natural logarithm. And then, of course, the negative goes to the other side, which means it goes to the exponent, which will flip this fraction around. Just quickly reiterating, remember, from core mathematics, swap x and y, and then go about making y the subject of the formula. And there you just need a good understanding and a deep knowledge of ln and e. Then example 5, we're going to solve for some equations involving e. I hope that all of you will recognize that this is 2:1, the exponent, which means it's a quadratic, so it's a k method. You can use k method, or you can see that this factorizes quite nicely. So you should get e to the x minus 5, e to the x plus 1. Solve for each. E to the x is 5, so therefore the x is the ln of 5, which I've gone in further with my calculator. Please just remember that you can't ever raise any positive base to an exponent and get a negative number. If you try to solve that in a calculator, it will tell you maths error. There is no solution over here. Nearly there. Example 6. I hope that you recognize that there is something special involving these two terms, the log of x base e, the log of e base x. I know I've said log over here. There's a reason, because I wanted that base x. You should recognize, okay, that these two things can be swapped around. It is one of the applications of the change of base law. Know the two fundamental principles of the change of base law and how it can be applied. So over here, log of e base x can be written as 1 over the log of x base e. And then we recognize that that and that are the same thing, which means I can make a clever k substitution, and then I can go and solve. So I've got k plus 1 over k is equal to 2 comma 5. You would normally multiply everything by k to flatten the expression. I've decided to multiply by 2k because then it means that this becomes 5. Okay, so it was just a way of getting rid of the fractions. And in the process here, I'm going to get 2k squared times that. I'm going to get 5k, bring it over, minus 5k, times this by 2k. The k at the bottom cancels. I get my quadratic. K is equal to half, k is 2. Remembering that k was the log or the ln of x. And so if it's the ln of x, x is equal to e to the power of 0,5, and anything power of 0,5 or half is a root, or x is equal to e to the power of 2. And then finally, or no, penultimately, here's a nasty one, where we've got to say to ourselves, well, we've got the ln as the exponent, I've got e's, I've got all sorts of things. Sometimes a very clever trick is to take the log of both sides of an equation. So if I take the ln of the left and I take the ln of the right, using my log laws, if you've got the product of two terms, that is the same as the sum of their two logs. And then over here, I've got the ln of e to the ln x. This ln x can come to the front using that power law. And then we're going to have a ln times a ln, which is the ln squared. Here, I can bring this 2 to the front. The ln of e would just be 1, so I've got that 2. And then very quickly, we should recognize that we've got some kind of quadratic, a little bit disguised. But if you go k method, k squared minus k minus 2, so k is 2 or minus 1. And then from here, if k is 2, where k was the ln of x is e squared, or x is e to the negative 1, which we can write as 1 over x. Again, I know I'm going fairly quickly, so in your own time, watch this video a few times and ensure that you understand this clever trick of taking the log of both sides so that you can open up the expression and you could bring this power back to the front. And then finally, we're going to talk about an exponential growth model. So there's a long story here, and we're talking about the mass of something versus the initial mass based on some constant multiple and some time factor. So I'll read it very quickly. The mass of a radioactive substance decreases exponentially with time according to the equation m equals m0, or initial m, e to the negative kt, where m0 is the amount of radioactive substance at t equals 0. So that is the initial at t is equal to 0, and k is a positive constant that depends on the type of radioactive substance. So it says, assume that you start with 20 milligrams. So I could go m0 is 20. Find k, so I know what I'm going to go and solve for. If the half-life of carbon is 5,600 years. Half-life, what the heck is that? Well, we define it. The half-life is the time it takes for half of the mass to decay. Okay, so half of this will decay. This over here is your t. So look what I've done over here. I've taken out, there is my t value. It was really up to you. You could have said the m0 was 20 and therefore the m value will be 10. But it's also quite easy for me to say, well, it's going to be half. It's going to divide by a half. You could have put the m just as a half. You could have put the m as 10 and the m0 as 20. But we're going to get this constant ratio here. And then we just need to go and solve for the k. If this were me in a matric exam right now, I would go and solve using a calculator. But I've just shown the steps. So if you've got this e, the base will become that base over there. So it's the natural logarithm of 0,5, and then divide through by the negative 5,600 to get your value of k. Remember, this is the exact answer. This is a rounded off answer depending on what the examiner wanted me to round to, whatever number of decimal places. And then finally, last question. Here it says to me, a bone is found with 30% of its carbon-14 remaining. How old is the bone? How old? Okay, that would be the t. Remember, we found the k in the previous example, so we do have the k. A bone is found with 30%. How old? Well, m0 would be 100% because I've gone to m, which is 30%. So we can just go and create an equation saying we've gone from the full amount down to 30%. How long did that take, or how old is the bone? Over here, instead of using the rounded value, I've just put in the exact value for k. And it's at this point that I would just go again and use a calculator there. But I've shown a couple of steps. The base becomes that base over there, so it's the ln. Then you would go and divide that underneath the ln, and you find out that the answer is 9.7 years old. Okay, so that in a nutshell is the grade 11 algebra. Have a break. You've deserved a break, and then you're going to go into the next set of lectures. Thank you so much.